Okay. Assume that's working. And present. Okay, great. Well, we are meeting. Now, let me explain why we did this. I don't think it's not, to me, it's not completely obviously clear that we need to not be meeting face to face. So I feel like this fits under the category of potential overreaction, but we want to err to the side of safety. I don't know if anyone here had the opportunity to read through Jeremy Howard's post. I think from my point of view, now is the time to be particularly careful. And so I'm chalking this up to that. I also think it's perfectly reasonable for us to have online meetings. Even in the best of times, I think we should have more of these. They're easy to host. We don't need to worry about venues. I'm not suggesting for a minute that we stop having face-to-face meetings, but we can have more meetings. We can have more informal ad hoc meetings. If somebody wants to give a presentation, it's no big deal. So I think this is a nice opportunity both to exercise a bit of proactive leadership in our community and not have face-to-face meetings during this somewhat uncertain and tumultuous time. So there's that. But also I think it's just plain, good to be innovative. And so let's treat this as an experiment and see how it works. So that's my kind of explanation for what's going on with this this particular format. This is being recorded, so we will have. I feel like I should verify that this is being recorded. Let me just double check. Pause share. Stop video. How do I know? Okay, it's being recorded. Good. All right. So Chicago ML. This is a joint meetup between Chicago ML and GoTo Nights Chicago. There's going to be a presentation by Mary from GoTo briefly shortly. So Chicago ML is a community of machine learning practitioners, Chicagoland area, obviously. We have a Slack workspace, so Slack channels. You can get to that with using the bit.ly URL chicago-ml-slack. We have a couple meetings coming up, and those are both going to be online. So we're going to do this through the month of March. We'll see how April goes, etc. So you've heard my spiel there. Okay, so with that, let me give you a quick background. Gray Matter went, did some extraordinary feats to get us a space that we politely declined this morning or last night due to this situation, this health situation. So I want to thank them for what they did, and I sort of apologize for this last second change. You understand why the change is. I think we're all in agreement that this is, at worst being overcautious. So I wanted to give Fred from Gray Matter a few minutes here to introduce Gray Matter and share with us what they're doing. So Fred.
Hey Garrett, thanks for the shout out. We appreciate it. If you ever want to partner in the future, we'd love to do it. So yeah, I'm Fred with Gray Matter Analytics in Chicago, Illinois. We're a healthcare analytics company solving real-world problems for a number of national payer and provider clients. It's a unique arena to work in among a variety of domain experts spanning the breadth of the healthcare industry. I actually started out in medicine, got my MD before transitioning to data science at Gray Matter. So what do? Our work focuses on integrating disparate sources of heterogeneous data and turning it into analytic solutions on a scalable platform at the enterprise level. Working and collaborating at the intersection of analytics and software engineering is at the core of our business model. And to remain competitive as data scientists, we increasingly lean on our engineering capabilities to meet the rising expectations for delivering stable, scalable, production-ready solutions. So that's why we're super excited to join in on this opportunity to learn how we can do better to bridge the gap between data science and software engineering. So very much looking forward to hearing from Garrett on today's highly relevant topic. Thanks.
Cool, great. Well, thanks, Fred, and thanks again to your team for all their work. It's definitely appreciated. And we look forward to more. Could be online, could be face to face. Who knows? But definitely more in the future. Like I said, this is a joint meetup between GoTo Nights Chicago, and GoTo is a conference. It's a really fantastic conference, and they have locations all over the world. We have one coming up in Chicago in late April. And Mary, would you like to share some information about the upcoming conference?
Hi, Garrett. Thank you so much. I think that there is an echo. I'm getting a few messages that there is an echo. So can you, Garrett, mute your mic for a second?
Oh, yeah. Sorry about that. That's me. Okay, so let's try that.
Okay, so hello, everyone. Thank you so much for attending the event tonight. Yes, no echo. Okay, great. Thank you so much for attending our first virtual event tonight with Chicago ML user group. We're happy to try new things out. My name is Mary. I'm the community coordinator for GoTo Chicago. As Gary mentioned it, GoTo Chicago is a conference taking place in April in Chicago at the Navy Pier. From the 27th to the 29th, it is a software development conference made by developers for developers. When we bring top speakers to cover topics such as, can I go to the next slide, Garrett, please? So you can check here the topics we have. We have data streams and pipelines, cybersecurity, distributed computer scalability, DevOps, team performance, microservices, languages, pretty much a bunch of field to cover on the software engineering. And then we also are bringing the top speakers on the next slide. You can take a look. And those speakers are Brian Goetz for Java, Anita Sengupta, which is a rocket scientist, Dean Wampler, who he had previously had a GoTo Night with us, Adam Thornhill, Bruce Lawson, and Jessica Kier. And you can check it out at the gotochicago.com. The end of the sales, early bird sales, ends tomorrow, Wednesday. And you can also get an additional 10% discount code with the GoTo Night 10 or the GoTo discount code from the Chicago ML or any of our media partners that are listed on our website. So thank you for them as well. We're also open to suggestions on what topics you would like to see at our GoTo Nights. So feel free to send that over on the email or on the Meetup page. I'll be happy to discuss that over with my team. As Garrett said, use the chat for any questions you may have during the talk. I'm gonna be interrupting Garrett during his amazing talk to ask these amazing questions. So feel free to ask any questions and I'll be able to just like pass the message over. Without anything else to say, just enjoy the talk. Thanks for attending this virtual event. Let's see how it goes. And thanks to Chicago ML.
Great. Well, thanks, Mary, and thank you, Fred. Okay, so about me. So I'm sort of representing the bridge here from the programming side, but I've pretty much my entire career been building software. Recently now going on 4 years, have been working in this sort of middle ground between the data science side and the engineering side, the deployment side. In building tools and supporting application development of data, we call data-enabled applications or machine learned functions in a particular application. So before that, I spent time at CloudBees, which is the Jenkins, Enterprise Jenkins company, on their operations side. So it was actually came by way of an acquisition, co-founded a company called Stacks Networks. And my job at CloudBees during that time was operational. So I have both sort of a programming and engineering bent, but also a lot of scars and wounds and sensitivities related to keeping software running. So a lot of what you're going to hear today is operational or production heavy. And that's a bias. I'm going to put that right out there. So you're going to get a particular bent here that is not your typical discussion when it comes to data science and machine learned applications. That said, I think it needs to be, there needs to be more of this discussion. So hopefully we'll kind of box this as I'm going to put out some ideas. They come from my history and my intuition. But really, I feel like this is completely an ongoing discussion. And I don't think that the things I'm going to be talking about here are really set in stone. So I'm going to put them forward as kind of my best guess. So hopefully at the end, we can have a discussion or even throughout. And I definitely encourage you to, if you've got a question or a comment, type it into the chat, and Mary will interrupt me, and we can stop and discuss that. Okay, so what about this gap between data science and engineering? This is what I'm talking about visually. You can imagine it. Now you can see it. We've got the data science side and the engineering side. Data science, I usually ask the question or show of hands, who's sort of on which of the two sides, and generally it's a discrete mix. There's not a lot of overlap, and there are reasons for that. These are very different fields, very different disciplines, requiring sort of different skill sets, and they're significantly different. There's a big gap between these two camps, and when we work together to build software, this bridging problem is a problem. It is a problem. I see it literally in every single attempt to integrate data science efforts and engineering efforts. So this thing exists, and I'm going to talk about how to bridge that. Okay, so some of the differences between the two, I have a bit of a data dump here. This is a bit of a complex slide. On the left side, I have kind of the different qualities, and then there are two columns. One is sort of the nature of data science, the data science artifacts, or I call it code here, and then traditional software. So in data science, a lot of the work, if not all of the work, is pretty experimental. You're doing novel development, both with novel data sets and approaches to building useful functions with that data. So there's a lot of experimentation. Traditional software is much more about laying down software for the long haul. So a lot of thinking about quality, testing, sort of stability of a system. That's the mindset of a traditional software engineer, different from data scientists. The destination, this is the second line here. Where does this code land when you're a data scientist, when you're doing your work? Where does this land? Now, historically, it often lands as a report. So you publish a finding. Now, I'm not talking about research. I'm talking about within an organization. So it's sort of a business analytics or a business intelligence application is really a report of sorts. Maybe it's interactive and dynamic, but it is meant to convey information, valuable information, but it's not software. It's not running in production someplace typically. Another format is a notebook. Same idea. You're publishing some kind of content. And there are exceptions to this, but by and large, historically, I think it's fair to say that the traditional data science output is in this area of information. And now that's changing. So this is why we're talking about this stuff. Collaboration between data scientists, generally I see one or two working together. I don't see a team of 5 working together on the same problem. Now that does exist, but by and large, my observation is that data scientists generally work either by themselves or with 1 or 2 collaborators. Traditional software is very different. These teams can scale from single digits to dozens very, very easily. And so there are unique problems related to the scale of collaboration in traditional software. The evolvability, now what I mean by that is, once you've done something, how much is it going to change and how often? I'm waving hand here. I know there are exceptions to this, but again, in my experience, data science output tends to be, here is my finding, and that's it, period. You want a different finding, I'm going to go redo this work, and it's basically a different project. Software traditionally, there's a huge evolvability factor. You're always changing the software. You're always evolving gradually to improve, add features, fix bugs. And so the processes and the tooling around this cater to that evolvability. And finally, the complexity. What are you building? In data science, it tends to be relatively less complex than in traditional software, where the complexity can really get to be quite insane. So this is not meant to be a calculus. This is sort of a hand-wavy generalization, but by and large, these are sort of informative points of these two camps, and it explains the big differences. And we'll get into some of those specifically. Now, this was a huge revelation. Now, this is a data scientist one of Guild AI's data scientists. And when I first heard him say this, I really stopped in my tracks, because everything that I knew or I thought I knew in that conversation, because we were having a debate about something, and I just stopped talking, because I realized that there's something I didn't understand about his work. And this is early on, so I've since gotten the religion here. But this is an extraordinary claim. I've talked to other data scientists, and roughly they say the same thing, maybe not quite 70%, but half is probably not that controversial. There's a tremendous amount of experimentation that goes on and uncertainty that goes on in the practice of a data scientist. And that fact alone changes everything in terms of process, methodology, how work is done and how work is delivered. And so it creates a sort of distinctive challenge. And what I'm going to be talking about in this presentation is how to recognize this, how to work within these constraints, but move the data science work into more of the traditional realm of software. So we'll see what that looks like, and we'll see if we can persuade you of this. For the sake of this discussion, I'm referring to a model as a software program. Now that's a bit of a stretch, or it's not, I mean, not a stretch. It's kind of a useless statement. You know, it's like saying it's a function or it does something. What I mean by this is I don't really care what the model is, what it does. To me, it's another piece of software. And I'm coming from an engineering background here. So I think of it as, here's some code, I got to run it, it's going to get some inputs, and it's going to generate some outputs, and that's software to me. I don't, how pedantically you want to explain what that is in the middle, I don't really care. Now, if you go to try to answer the question, what is a model? I've done that. You're going to get all sorts of stuff through the internet. I don't think there's a single answer. So what I'm saying here is, for the purposes of this discussion, I am strongly biasing this debate into the software realm. All right, you're going to see where this goes. Okay, so what is model development? Here are some examples of what models typically do. These are just examples. Models can do all sorts of things. Predict a price, classify an image, track objects in a video stream, paint pictures, translate text into other languages, all sorts of stuff. And generally what we're talking about when we're talking about a model versus, maybe a traditional software program, is we're talking about a task here that is really, really challenging to perform without the model. So the model introduces an innovative way to program that is otherwise, that without that innovation is otherwise very difficult, if not impossible. So models are distinct from traditional software. So it isn't just a program, but it's a program that has to go through this data science magic, black magic. And it does some pretty fantastic things. And I bet you the reason that you're sitting here, standing here, you're part of this community of machine learning community in Chicago or wherever, is because you're interested in harnessing the fantastic power of machine learning, data modeling, what's going on in data science. So there is a distinction, but it's first and foremost software. So as an example of a manual program, this is kind of classic computer vision. These are hard features that try to define some primitive aspects of a bitmap. So it looks for edges, it looks for lines, and it looks for relationships, very simplistic center relationships, and then this four rectangle feature. And this can be used to do basic object detection or classification within an image. All of these features are manually engineered. Somebody said, hey, look, if we break this image down into lines, edges, and different relationships, we can make inferences about what is in this image. And so it's a very sort of reasonable approach, a direct approach. If I were to sit down and say, I'm going to program this thing, I might be inclined to think of it this way. I might borrow this. But this is how this evolved. Somebody said, how would you do this? And then you reason through an algorithm or an approach, and then you manually implemented it. That's a model. This is a model. Or features. This is a totally legitimate way to go about detecting objects in an image. The modern take on this is a learned program. And so here we're looking at different layers in a convolutional neural network. Most of you have probably seen this. These are the same idea. You have features, just like this. You've got lines and edges and relationships. Here you have features, but they were never taught, or they were never explicitly programmed. They were learned. So what happens here is you have a model representation, you feed it examples, and it learns on the left side these primitive lines and edges, in the middle higher level representations, and then ultimately can detect faces from an object. So this is kind of the magic of machine learning. But to me, this is all fundamentally we're building software, just a different approach. So the process that we're looking at here is a data scientist generally will embark on a process of exploration, which will consist of looking at data, working with data, trying different approaches to perform a task that he or she wants to perform. Notebooks are a common, I'm talking about Python, R, same idea. There's this sort of ideal environment or good environment for data exploration and experimentation. And out of that comes some working code. I'm not talking about the quality of the code or how modular it is, or it works. It's working code, great. That, when we deploy this, goes through this process. So this is the line going to the right. We need to come out of that process with an artifact that we can run. So we're generally looking at source code or an executable graph, for example, TensorFlow, PyTorch. They use underlying computational graphs. Along with that will be trained weights or perhaps data that will drive prediction or whatever task the models perform, and then the runtime libraries. With that, we've got a quote-unquote model. With that model, we can then move into production, where we're talking about a runtime environment, monitoring both from a latency standpoint and an accuracy standpoint, and then topics surrounding availability and recovery. This is, the basics, kind of the basics. That line there, the second two parts, the model, artifact, and production, are often novel and new to data scientists building applications. And this gets back to my original premise of what the sort of the goal of the generated artifact from a data scientist. The artifact being a notebook or a document doesn't really have to be published as an artifact or released as an artifact, and it's not going to go into production. So don't worry about it. So this new stuff.
Questions here.
Yeah.
So by notebook, you mean a paper-bound spiral notebook, or is it a technical term?
Sorry, yeah, it's a technical term. A Jupyter notebook is what I meant.
Okay, thank you. Jupyter is so ubiquitous now that people just started calling them notebooks. So I should probably put Jupyter in there. But it's a tool. It's a piece of software that you run that allows you to iteratively execute code in cells and evaluate the results and print results sort of in a sequential flow of information. So it's a common tool used by data scientists for exploration and working out theories and experimenting with things and trying different things. Out of that, though, will come some code that you can run. So I would say 9 times out of 10, the data scientists that we're working with will end there. So they'll end on this, I don't know if you can see my cursor, but they'll end on the left side. And then they'll hand off in some fashion to what you might call a machine learning engineer or a software engineer who will have to work out the details of what it means to run this code. Great, you've done this amazing work. How do we run it? And there's all sorts of technical details to work out there. And then, once we've worked out those details, to actually put it in production in a way that it runs. It runs at all, it runs well, it can be upgraded. If there are bugs, we can fix it. There's a lot of complexity that starts to roll out as you move along that arrow. That's the process. Is the assumption that Notepad can be used in production?
Well, that's a great question. So as I understood the question is can you just put the notebook in production? And there are people who are certainly trying to do that. My answer would be that's a terrible idea, and I would not. Now I'm a big fan of trying things. So if somebody were to really committed to trying that, say go for it. But I think that there are problems galore, not just associated with the runtime, but the actual code and maintenance of the code. And we'll get into that. So we're going to get into sort of some of the bigger problems that arise here, which drive a different approach. Okay, so here's an example of a production dashboard. And I borrowed an image here from Datadog, who's a commercial vendor, and I'm not really plugging them. I've used Datadog. There's a bunch of different monitoring and status dashboards for operations. The point of this image is just to show that there's a whole job description, which is to make sure stuff runs and runs within service level agreements, within SLAs. And this is something that is new to the data scientist. What does it mean to deploy your code in production and make sure that it runs, and make sure that it runs within an acceptable time frame, and make sure that it runs correctly? And if there's a bug, how do we update it? How do we make sure that that system is available? Now, I'm not assuming that every system is online. Every system is networked. In this case, we're looking at I don't know what we're looking at here, and we're looking at general metrics. But the idea of running something in a production setting is standard across any application. And what that means is it's real. People are using it. And maybe it's a mobile app. Maybe your work product is running disconnected someplace. That's still a production setting. And you still need to address production issues there. And there's just no way around it. If you're building stuff for real, I don't mean to denigrate researchers or people who are experimenting or publishing, and they stop short of deployed application. That's what drives everything. That's the centerpiece of this field. So I'm not trying to denigrate that. But the point of this whole discussion, this whole presentation, is when you need to push that out and run it, how does that whole thing work? How does that whole end-to-end cycle work? And the idea of production from a data scientist standpoint is fairly novel. And there's a lot to learn there. There's a lot to be exposed to. So this is a little snippet of that. When we talk about production, we're generally talking about a system or functionality that needs to be available. That means it needs to run. What is this? There's lines over here. I don't know what this is. Sorry, I got distracted by two lines. It looks like somebody scratched my screen. Oh, can I draw on here? Sorry, I got completely distracted. I don't know what that is. Okay, we'll edit all this nonsense out, maybe, probably not. Okay, availability. When we're talking about a system that's available, here are some of the components that we talk about. Servers are running. Are the servers plugged in? Usually there's a data center that's involved, so we don't have to worry about that. Is the data center available? There's networking, so there's cables and there's electrons running through wires. There are services running on these servers. The services here would be operating system processes that need to be alive and responsive. Assuming all of that happens, what is the response time of the service? How quickly are we getting a response back? Is it 3 seconds? Is it 30 seconds? Is it 3 minutes? Or is it a nice snappy 30 milliseconds? Depending on your application, that is a very important consideration. And it directly maps to availability. A slowly responding application can be deemed not available, even though it's responding. If something is taking more than an allocated amount of time, that system can be considered down, not available. Then, of course, the content. Is what's being served accurate? Is it correct? Is there a bug there? Is it useful? All of these things are considerations when it comes to the availability of the software that you're building. And you can't hand wave around this stuff. If it's going to work, you have to address all of these issues and then some. But these are the topics that make the problem really quite complex in the end, to deliver that functionality to the end user. So what we're dealing with here are really two sides, two very different points of view. One comes from the data scientist, which is inherently exploratory and involves a great deal of uncertainty. So, even if half of your work product, hits the cutting floor, it doesn't make the grade because you're searching for something. Even half, that is an incredible dynamic. That is not the case for typical software. If a software developer is throwing away half of his or her code, there's a serious problem there. I'm not sure what's going on. That's a broken system, I think. So for software developers, the idea of repeating something and being certain about something is paramount. So these are very different worldviews, and they're legitimately different. You cannot force a data scientist to rigorously be repeatable and certain in the face of uncertainty. And similarly, on the software side, you cannot be okay with I'll sort of play I'll troll slightly. You cannot hand them a notebook and say run this in production, because there are technical problems that cause that to be a very bad idea. I can defend that. Maybe there's time at the end we could talk about some of those details. Okay, so let me just skip to this. When you make a change to a system, right, and this could be, I'll flip back to the other slide, it could be any number of things, and I'll get into that. The question you should always ask is, did I fix it or did I break it? And this is neither a data scientist nor a software engineer. It's everybody. Everybody who touches a system makes a change. Did I fix it or did I break it? You cannot get around this problem. This is the centerpiece of the problem, because you need to change. The things that you're changing are the model architecture. Now we're talking about the model part here. We're doing data science, data-enabled apps here. So we're talking about model architecture, how the model is learned, so the learning algorithm, the code, the logic, the transformations that are applied when you load the data and clean the data. How are you engineering features? There's always some sort of feature engineering. There's always some level of decision making to improve what the model learns from. So you can change any of that. And then finally, and this is big, changes to the training and test example. So this is the data that you're feeding the model as it learns. Any one of these things changes. Anything changes. This is the question. Did it get better or did it get worse? And as obvious as this probably is, it's completely obvious. You make a change, you got to answer the question, did I fix it or did I break it? The hard reality is, in data-enabled apps, this question is not answered. You don't know. There's intuition. I believe that I fixed this. It looks good, right? If you are a software developer, this is like making a change to code and being very confident or reasonably confident that it fixed the problem and it didn't break something. And if you've ever built software, you know that is a terrible feeling, because you probably broke it. You probably did something to break something. And that's why we do tests. So I want to talk about test-driven development. I also want to clean these lines up. Does anybody know why these lines are here? Can you see the lines?
Yeah, you draw it. So you
I don't know.
Where you can just
my OCD is kicking in, and I just feel like I must fix this. I mean, I can live with it. I don't know how to fix it. Oh well. It's part of the rustic, handmade feel of this presentation. So 2 scratch marks and then a little scratch mark. Okay.
So annotate at the top.
What's that?
At the top, it says annotate.
Oh, annotation. Oh, can I clean this up then? Oh, great. Clear all drawings. Haha, thank you so much. Okay, great. Now I just need to not do that again, however that happened. Okay, so I'm going to talk about test-driven development. Test-driven development is a mainstay of any successful software project. I just don't, I feel like if it's successful, somebody's doing test-driven development, even if it isn't really even if it's not by name, in spirit, they're doing something that's basically like test-driven development. It is, I just can't imagine building software without using tests as a centerpiece to measure progress, to measure the correctness of a running system. Now there are type systems, there are linters, there's all sorts of things that can analyze code. Languages like functional languages with strong type systems like Haskell will get you a long ways in terms of being correct before you start testing. But even those applications need to be tested. There's different ways of testing it, but testing is the centerpiece of effective software development. So what I want to do is I want to map the virtues of test-driven development to the data science function. I want to see, are there ways, can we just do test-driven development from data science? The answer is you can't. You cannot do that. It is not the same thing for the reasons that we talked about earlier, being very different, fundamentally different types of work. But I believe that there's a lot to be learned, and I believe we can get pretty close. So I'm going to talk about that. All right. What is test-driven development? Well, test-driven development, I've really distilled this here. You've got 3 points. You write a minimal failing test. It doesn't have to necessarily be failing, but you write a small test. It should be very small and isolated. And then you write just enough code to make that test pass. And then you keep doing that. And the insane magic of this is this is this 3 simple process. If you keep doing this, you're going to have, unless, assuming your tests are on point, you're going to have working software. Now that's a bit of a hand wave as well. But basically that's true. This is a very, very effective way to build robust software. So to quote Kent Beck, accredited with the invention or the naming or the formalization of this method. If you're happy slamming some code together that more or less works, and you're happy never looking at the result again, then test-driven development is not for you. He's being a little cheeky there. Test-driven development rests on a charmingly naive geekoid assumption that if you write better code, you'll be more successful. TDD helps you pay attention to the right issues at the right time, so you can make your designs cleaner. You can refine your designs as you learn. All right, this is from Michael Feathers, who I believe is for some reason I feel like he's a routine go-to speaker. If not, I've got my conferences wrong. Code without tests is bad code. I would agree with that. It doesn't matter how well it's written. It doesn't matter how pretty or object-oriented or well encapsulated it is. With tests, we can change the behavior of our code quickly and verifiably. Without them, we really don't know if our code is getting better or worse, right? And that's that question. When you make a change, did I fix it or did I break it? And Feathers here is saying, look, the answer is you got to test. You have to have tests, and you run the tests, and they'll tell you. If it's broken, if you broke something, your test will tell you, and that is the case. Without this sort of fundamental precept of building software, which models are, right? Models are software. Without this fundamental precept, you don't know whether you're making it better or worse. And the problem here is, how do we apply that effectively to model development? This is an aside. I'm not going to spend a lot of time on this. I was looking for data, like research data on, does this stuff work or not? And this is kind of a nice graphic, a summary from this effects of test-driven development that show that there's a trade-off. And the white here is good. The black part is bad as a cost, sort of negative, and the gray is sort of neutral or inconclusive. That effort line, I think, is probably wrong, is mismeasured. I feel while there is effort put into test-driven development, the effort that is involved when you don't have tests is got to be much, much bigger, because your code is going to be terrible. You're going to constantly break things, and you're constantly chasing down bugs. There's no way that effort is a negative for test-driven development. And I admit that's confirmation bias. I would reject that finding based upon my formative intuition on software. Tell that to the research. Tell that to the scientific method. Okay, anyway, that's an aside, and you can follow these links to get more. This is an old study, by the way. This is 2014, so I don't know if there's more current, but it's an interesting topic for research. Okay, so the challenge is applying TDD to model development. In test-driven development, you kind of want, when you're building software, you're making an assertion right away about the result. That is sort of by definition, you're saying it should be this. But then when you're doing data science work, that initial exploration is uncertain. So you're not going to go lay down a bunch of tests when you're not even sure what's going on. So it's inherently non-test worthy to start. And the question is, at what point do you start to now want to test? And there is a point that you need to start to test. And we'll kind of get into that. I'm going to reframe this problem a little bit. So not only is it, the initial results are uncertain, but the results are usually, often non-deterministic. Or let's say they're easily non-deterministic. You have to be very, very careful to be deterministic. And some models are simply not deterministic. So you cannot say, I assert the value is this. And if you did, it wouldn't mean anything anyway, because the models are generally, you're building models within a realm of statistical probability, of a distribution. There is no value. There is a distribution of values. And so the method of testing or making assertions on model behavior has to be different than traditional software. Another challenge is that the operations, the things that you do in data science, can often be very long running. So for example, I'm going to train a model on 100 million rows of data. Well, 100 million is a big number, and no matter how fast your system is, it's going to take a long time to process 100 million of anything. You might have a fast system where you can do it in a few seconds or a half a minute, but chances are, if you have a traditional system, and especially if you're reading from disk, that's going to take a while. You might be sitting there loading and processing things for 20, 30 minutes or more. It's very, very difficult to run a traditional test-driven development method on something that takes 20 minutes. And this was the debate that I got into with our data scientist. He's like, yeah, you can't do that. You can't do what you do. You're doing stuff. Your problem is easy. My problem is hard. Then I saw that. I'm like, okay, you're right. You win the argument, but I've since changed my mind. So I'm going to tell you what I think there. And then finally, you've got these state dependencies. So you have these chains of things that you're going to take a half an hour to load a data set, and then you're going to use that to train a model. How do you iteratively and rapidly train something when your data takes that long to load? So there's some real problems, challenges that test-driven development faces when applied to data science. So what I want to do here is I want to change the vernacular. I want to change the way we talk about these things. So rather than talking about tests, I want to talk about experiments. And rather than talking about test failures, which is generally an assertion of a value of a Boolean state, is this value this or that, we're going to talk about outliers, which has a statistical connotation. And finally, for test coverage, so when we're talking about testing a system, testing our models, we just can't test exhaustively for many, many reasons. There are subsampling strategies. So we're looking at this a bit more from a statistical standpoint than the traditional exhaustive search methodology that you see in test-driven development. Now, I would typically stop here and ask for questions, but I'm going to trust that if you want to break in here, that you're gonna. I feel like this slide is worthy of some questions. So if you think of them, please be brave and type them in, and I'll stop and we'll talk about them. Okay, so test-driven development, model development. Here's the method that I would recommend as of today. Who knows how this will change. First and foremost, you want to define your metrics of success. So you want to understand what it is that makes a good model or not. This is effectively your test. So accuracy, area under the curve, MSE, mean squared error, other stakeholder key performance indicators. It could be conversion rates or things that are meaningful to stakeholders. Whatever they are, you want to identify them and identify a way to measure them. So once you have that, you have sort of your target. This is the kind of thing that you're either optimize, you're trying to maximize or minimize. Second, you want to define the operations. So understand what your workflow is from I'm doing this. Like, this is what I'm doing here. I'm cleaning my data. I'm loading the data. I'm generating features. I'm going to train a model. These are discrete operations. Generally in notebooks, these things are an amalgamation. They're in a big litany of code, big wall. I call it a wall of code. And they're in there someplace. We want to formally define them. We want to reason about them and call them operations. I'll give you examples of this in a minute. Next, we want to be able to run these operations as experiments. We want to do it and we want to record the results. And we want to do this when we start, soon, not later. Because what we want to do is get to the point where we're running these kind of like tests and we're running them all the time. We're rapidly running them. So we easily run them, we run them iteratively, and we look for improvements and we look for regressions. So is it getting better or is it getting worse? And then sort of as a final point, to do this effectively without losing your mind, you want to minimize the amount of time it takes to run these things. And I have a discussion in a little bit about what we're calling a 10-second rule. Okay, here are my best practices within this kind of system, this regime that I'm trying to present here. Okay, so I'm going to be talking about code factoring, linting, tests, experiment tracking, the principle of small being better. I could say small/fast being better. I have a very strong point of view about notebooks. I started out being strongly against them, and then I changed to be like strongly for them, and now I'm strongly against them. I should say I'm strongly against them being used in a particular way. So I will explain what I mean by that. And then finally, joint code ownership. So let's get into this. Okay, so code factoring. I have as a parenthetical here, I'm going to kind of assume that we're starting with a notebook, which is generally just, hey, I got this to work. And I really don't mean to suggest that that is not outstanding. Like, that's it. When you get your stuff to work, as a data scientist, you're getting a good result. It doesn't honestly matter how good or bad the code is. You're proving so many things in that litany of code. So I don't mean to suggest that the litany of code is a problem in and of itself. It becomes a problem when we stop with the litany, with the wall of code. We need to push forward, and I'll show you why. When you push forward, you get to this process. By the way, this is the slide. This is the slide. I could say that, this is sort of one of the more important slides. It would be this one. This kind of rapid, iterative, experimental, measurement-oriented approach. We want that for the data science function. Okay, so we don't want notebooks. So automate the operations with command line interfaces. I'll give you an example of that. We want to define our thinking/decisions with functions. I'll explain what I mean by that. It's a little cryptic. And then finally, we want to reuse our code with shared modules. Here's an example. So this is a Python script. I've named it train.py. You don't know that. I mean, just trust me. This is code. So I've got two, it wraps. So this is like a window and it wraps. This is all one module called train.py. When you read a Python module in this format, this sort of if name equals main, if you're not familiar with Python, even if you are familiar, this may look unfamiliar. This is a way to sort of allow a module to be used both as a module and also as a script. So it can be run from the command line. It can also be imported without executing. So what we do is we tuck all of our execution functionality into functions, and then we call usually a main function or some entry point when the name of the module is specified as under main. That is the case when you run something from the command line. So what we're doing here is we're taking our wall of code. Assume this was a wall of code with lots of detail. We're defining functions. It's in a module. I'll get into this command line interface in a second. And then we're reusing codes through imports. And this is kind of the marker I like to see as a point of maturation. So we go from that wall of code from the notebook to something that looks like this. And something that starts to look like this. I'm like, okay, we are now approaching a point where the work product generated by a data scientist is now in sync with the work product that is created in sort of best practices by software engineering. And we're starting to bridge that gap, right? That gap now is, this is the same code ultimately that's in that notebook, but it's now in this format. That is a tremendous bridge that has occurred by this, what I'm calling a factoring or refactoring exercise. Okay, take a look at the CLI. CLI stands for Command Line Interface. In Python, there is a module called argparse. Every library that I know of, every language, has something that helps you parse command line arguments so that you can you can parameterize your script. So here we're parameterizing with two different parameters: the number of layers that our convolutional neural network is using, so we're defaulting to 3, and the location of our data. By doing this, we allow somebody from the outside to change these values without changing the code. This is generally not what you see. Well, you don't see it in notebooks because the notebooks are not run in the command line, they're run in the notebook. And what you'll see here, if you're lucky, is these parameters will be defined as global variables. Often they're just hard-coded right in the code. So what we want to do is pull these out and reason about these things and parameterize it. And this becomes part of your interface. So the CLI is command line interface. So right now we're starting to modularize and make our code reusable from the command line. And that's going to let us run this thing over and over and over again without thinking about it. We're just going to run commands. That's the function of the command line interface. The functions here are def, train. These are names. The one rule you can follow is keep your function small. Limit the number of lines of code in your function. If you can limit it to 2 or 3, that's pretty hardcore. I like to see that. If you have more than 10, danger. If you have 20, that function's too big. It's just too big. And there are some cases where it's tough to have a tight, small function. Python makes it hard. Some languages make it hard. 20, okay. If it's 40, no. That needs to be broken down. When you have a lot of lines of code in a function, you have a lot of decision-making and thinking and reasoning that's going on in there. You can pull each sort of discrete decision or reasoning bit, pull it out and put it in a function and call it. That is such an incredibly powerful pattern in software development. It forces you to think about your reasoning, and then it forces you to spell it out formally as a function. It is the miracle serum for creating quality code. And a data scientist can do it every bit as easily as a software engineer. It's still code, right? You're just having now to think about it and define your decision making, your reasoning by way of function definitions. And then finally, we're reusing. So there's some hand waving going on here. We're importing models, whatever that means. We're using a CNN. But you see here M equals models CNN. That is an example of code reuse. You can put your model definition behind a module and then reuse it. That, I think, is a nice to have. I think the two things that you want to see are put your stuff in a script, give that script a command line interface so that you can run it and parameterize it without changing the code, and use lots of small functions that define your logic or your thinking. Now, I hope there's a question at this point. Somebody type a question, please. We should have questions.
No questions.
Right, I'll continue, but I want to be interrupted soon. Can everyone still hear me? Is this on? Knock, knock, knock. All right, that's good. Okay, so that's sort of my lesson on factoring, and the goal here is to move the code toward a production state. And it's not simply a matter of having quote unquote clean code. It's a matter of having code that you can test and that evolves. Okay, so that when you make
the chat is now acting. So there is one question that says for up. I'm going to assume that is asking about functions, if that is okay, like for and up functions. If There is, can you talk more about if name equal to main? I understand it allows me to launch scripts from the CLI, but I do not understand why. So that will be the previous slide, I guess.
Sure. Yeah. No, it's here. The question, as I understand it, is about this sort of boilerplate weirdness down here. If under name equals quote under main, then call main. So when you load a Python function, when you load a Python module, the Python interpreter will execute every line as it sees it. So it goes, oh, import models, and then it will actually execute that code. And then it will, so this is an interpreter. So it will execute it will interpret each of the lines, each of the expressions in the order that it sees it. This def main is a definition of a function. So it's just going to define the function. So we're defining another function or defining another, all it does is define it, doesn't invoke it. So at the end here, it's going to execute this conditional statement, which is if name equals, it can run a test. And if that's true, it's going to call main. The only time that this is true is when you're running this script from a command line. It is not the case when you're importing it. The under name will be equal to train. So it will not execute. So depending on how you're loading the module, this will or will not execute. What you typically see when you're naively copying code from like a notebook into a script is that the script will always execute. Whenever you load it, it executes. So you're not defining a function, you're going to run the code all the time. That's not the end of the world, but that particular module is not reusable as a module because every time you import it, it's going to run. I just like to see this as a pattern. It's good practice. All modules should use this. I don't think there's any good reason to. I mean, unless you're just being quick and dirty, that's fine. I don't think this is not a big deal. I wouldn't get too hung up on this. The main point is you want a script, not a notebook. You want to look for command line interfaces. It's difficult to work with one of these scripts when you can't parameterize it, and then functions and then the reusable modules. Okay, so a few other things here. Python is a language that Guido van Rossum designed to be readable and and consistently written. So there's this is a very early PEP Python. What does PEP stand for? Proposal, Python, something. I don't know. Somebody knows what it is. They're probably typing in right now. Basically, these are proposals for different things in Python. So all changes to Python are driven through the PEP process. This is a very early one. Guido wrote it along with Barry and Nick. And it's the style guide. And the style guide is something that you can kind of enforce. There are formatters and linters that you can use. This is an ecosystem of linters. And these are programs that you run on your code, and it will tell you, hey, this isn't a good idea. You defined a variable here, but you never used it. So that's a mistake. You should never define a variable that you don't use. So either don't define it or use it. Python is a very lax language. It's very happy to run whatever you send it. As long as you're syntactically correct, it'll run. So it's very, 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 very easy to put bugs in Python code. Very easy. I would never consider ever not running linters on Python code. It's nuts because linters will find bugs and there's no reason not to run them. And that goes for everybody. This is one of the problems with notebooks.
Okay, I use yours.
Oh, we have someone.
I'm not sure if I should stop or is there a question here? Or? I'm going to continue. I'm not sure what that rustling is. Some rustling going on. Okay, linters. Data scientists use linters. You're going to find bugs. You don't want bugs in your code. I mean, bugs in a model are really tough because you're going to have a result that's wrong. Chances are it's wrong. So you want to catch these things. Linter will help you not be wrong in these cases. Tests. Lots of different ways of testing Python code. I wouldn't get super caught up in this. This is, of course, the mainstay of test-driven development, but I'm not really talking about these types of tests. But if you have code that can be tested, here's a factorial. That's a nice data science function. And we see here on the left side panel, we see the use of this factorial function inside of a document string. So this string here, this triple quote, is a string in Python. So this is just text. And it's called a doc string because it provides documentation. In that doc string are code examples that can actually be run and verified. It's a really cool feature of Python. In fact, our studio and our approach to our Markdown is very much inspired by this pattern in Python, which this has been around forever. It's a very nice way to test because you test, but also B, you document. So, but it is one way of testing. I would negotiate within your team, how do you guys want to test? This is a particular way. I like this approach. On the right side, we can see a test report. So we run tests against the code, and we can even measure how much test coverage we're running here. And then PyDoc, PDoc I have listed here, is a nice way to generate documentation, sort of browsable documentation from doc strings. These are things that are in some ways nice to have, but in systems that are more mature, where you really do need to, you want to really lock down, it becomes important to test basically all of your code in one form or another. And this is sort of the canonical way of, one of the canonical ways of testing Python code. Experiment tracking. Near and dear to my heart. Guild AI is an experiment tracking tool, so I have a lot of opinion about this stuff. I'm not talking about Guild here. In fact, I'm going out of my way not to. There was every once in a while, Reddit will have a big thread on what machine learning experiment tracking tools people use. I always like to weigh in on that, and it's a topic of passion of mine, and there's just not a lot of people who care about that. So whenever I get a chance to talk about it, I get pretty excited. This fellow, I assume, Sultani Yaga, and I apologize, I probably mispronounced that. This may not even be his name, it's his Reddit name. Anyway, he weighed in with a very thoughtful, and I thought very on point summary of the problems and desired features of experiment tracking. So I'm basically going to lift that from his post on Reddit, and there's a link there if you want to read the whole thing, and I have a response to it, which kind of highlights what I think are some really brilliant observations. So I'll go through these quickly. So in experiment tracking, what you're looking for is an experiment that sort of bundles a bunch of stuff together. And what you're bundling is the source code, the inputs, the command that you're running. What is the experiment?
Wouldn't a notebook environment help you link and test coding small units, as you seem to be speaking to?
There's apparently a notebook fan in the audience. I can't believe it. No, I mean, possibly. I mean, I haven't seen it. If you go search, so do this. Go search, test notebook, test Jupyter Notebook. Go read what's out there. There are a couple frameworks out there that people use. They're usually involving assertions. So there are ways to test Jupyter code, notebook code, certainly. There's a lot more robust ways and a lot more tooling to test non-Jupyter, traditional Python source code. I would use the latter. I wouldn't try to shoehorn a test regime into a notebook. So I was thinking of one other point here. Oh, the modularity that I'm advocating here. You can do that in a notebook, but you don't generally see it. You sure you can do it. But all the work that you're doing to refactor that code, I would put that into building traditional Python software. It's not just the notebook. It's not just the code, but it's software sitting in a canonical form that can be automated, that can be run from a command line, or a tool that runs the command line. It doesn't have to be a literal command line, but it can be executed. So for testing, etc. But this code can be run quickly and iteratively. Notebooks just don't do that. They just don't work that way. You got to click up on a cell, evaluate it, look at the result. What I'm talking about is a rapid fire approach that you make a code change, you run a command. You make a code change, you run a command, and you see the result. That pattern can be applied effectively in data science. It may not be as granular or as fast, and it's not the same types of testing. Here, I'm going to fill in this experiment tracking bit here so you understand what I'm talking about. But it's experiment oriented, it's measurement oriented, but it's essentially the same methodology and the same value proposition. You're experimenting with changes, you're measuring the impact of those changes using a test regime. So for model development, test regime maps to experiments. And to do that effectively, you need to track them. So we have an experiment that's this sort of black box, is what Sultani referred to it as. And you want to be able to completely measure from end to end what that experiment was. So you want to capture that operation that you ran at full fidelity. Once you capture that, you can use the results to analyze and summarize the model development over time. So you're doing this over and over and over again, and you're seeing, did this change make it better or worse? What does that mean? Did my metric go up or down? It's just that simple. If you have 10 metrics, then you've got trade-offs to look at. And you might have qualitative things to look at. You might be looking at plots. But the point is that you're measuring and that you're capturing this information and you're using it to inform your next decision. That is the essence of test-driven development. And we're applying that to model development. Okay, a few other points here. You trace the source code versions through experiments, so you have control, so you know this experiment came from this source code. And you can reuse artifacts. So this prepared data set was used by this training operation for training, but this data set was used for testing, and you know what was what. And it's not written down in a paper notebook or in a spreadsheet, but it is captured in full fidelity by the tooling that you run. That's the spirit of TDD. And then he mentions a few other things back up, and I've already mentioned the training and testing across different data sets. All right. Okay, I'm going to kind of speed up here because I want to wrap this up. There is a trend in data science which suggests that training big models and expensive models is somehow better. That is false. It's a bad idea to start with a big model because it makes you go slower. The value of small is that you can experiment and iterate, spending less cycles, compute cycles, and that means you can go faster. So the point is to drive your model development as quickly as possible. When you're sitting and presuming that you need a huge model to perform a task because you're fascinated by state-of-the-art benchmarks, I would suggest you not do that. I would suggest that you start with the simplest possible model that can solve your problem. Go fast, iterate quickly, live with not the best accuracy or performance results, but is it good enough? And then once you have that basis, you have a basis for systematically improving. Then you can move in to the deeper, more complex models, but you're doing it with a platform that's centered on iteration, measurement, and data-driven work. So with that in mind, this fellow Radek Osmulski published this blog post, How to Do Machine Learning Efficiently. And in that, he proposes this 10-second rule. And this, everybody should read this. It's a very good article. And this is sort of being taken up by the Fast AI community. So this is how I found out about it. So this is what it says, subset your data in a way that can create a representative sample. So rather than training on your full data set, subset it. Find something that's representative. It basically means randomly sample. So you're not going to train on the full thing, you're going to train on a small part of it. Keep running experiments, figuring out what works and what doesn't. Your fingers never leave the keyboard in a flow state. What he's describing is what most programmers are involved in with TDD, but he's basically mapping it to model development. So don't ever let calculations exceed 10 seconds while you work on a problem. And now maybe that's impossible, but I think that when you think about this, when you define this as a goal, what you're doing is saying my brain power, I should not be sitting around waiting for the computer to finish. So I'm going to orchestrate and define my problem such that I can get feedback within 10 seconds. Now, Hadley Wickham of R fame, I was very fortunate. I was able to sit down with dinner with him at a dinner table, and I asked him this question. And he basically said the same thing. He believes that, you know, you want to iteratively and continually change things. And sometimes if your data science problem is too big, you just go too slow. You've got to pare that problem down so that you can go fast. This is all very much in the spirit of TDD. All right, now notebooks bad as IDs. Finally, this is the part that everyone's waiting for. Okay, so here's why notebooks are bad, and this is this is taken from the trolling web or blog post 5 reasons why Jupyter notebooks suck. Now, I didn't write this. This is somebody else. That's what he named it. Some people like to get attention by having trolly titles, whatever. So I'm not bad mouthing notebooks, but I believe that notebooks as long running, as authoring tools for your code, it's a bad idea. Here's why. And this, I'm lifting this from his blog post. So it's almost impossible to enable good code versioning. That's true. This stuff is stored as JSON. All the diffing and code merging qualities that you're used to in code are gone unless things have changed within the last few weeks. There's no IDE integration, no linting, no code style correction. That's true. It's very hard to test this. You can do it, but it's hard and it's weird. You have this nonlinear workflow of Jupyter where people will think in this sort of way of like, I'm going to edit down here, I'm going to go up here, change a variable, execute that, then go down here, run something, and go. Terrible. I mean, it's in the spirit of test-driven development where everything is completely deterministic and repeatable and fast and runnable. This is anathema. It's the opposite of what you want to do. And finally, it's bad for running long asynchronous tasks. And what he's talking about there is production. And the question earlier was, can you run Jupyter notebooks in production? Sure, you can try. I would not. And if you're that determined, go for it, and then tell us how it works. I feel like you're going down the wrong path, but there are people who are doing it. So it's not, and I could very well be wrong here. You might see that notebooks evolve as a runtime platform. I mean, Python itself is not the greatest runtime platform, so who am I to judge Jupyter? If it works, then it works. So I would take my kind of religion here. If you feel compelled to drive forward with putting notebooks in production, I think I won't. I'd be curious to see what your result is, and genuinely curious. I'll be interested to see the lessons learned, what works, and what challenges you faced.
Working here with data engineers, how do you use your flow for writing DS project? I think you're mute.
Let me see. So this is the last. Oh, this is to me. What was which question are you? Although I looked at all these questions.
Oh, the golden right. I don't have access to the questions.
Oh, okay. Well, I know which one. Let's stick with the system here. What's the question from you, Mary?
Have you used Airflow for writing DS project?
Yeah. So Airflow is a nice orchestration tool that allows you to orchestrate workflows and more importantly, and probably most importantly, observe their status in a way that can be consumed by humans and by other systems. So it's a nice way to consolidate and centralize and orchestrate workflows. I'm not really talking about that here. I feel like that is a moving toward a production workflow that is kind of outside of the bridge problem that we're talking about. It's not directly related. I think that you want to get your workflows, your developer, local workflows as fast and iterative as possible. And I think the last thing you want to do is complicate that with an orchestration workflow system. It's that's nice for CI, for continuous integration, and it's nice for people to see the status of a pipeline. but that's more when you're looking to have a high ceremonial centralized function. What I'm talking about here is individual workflow and collaboration. Okay, I'll try to keep this up so I can, oh boy, look at all this. All right, I changed my mind. Mary, you can, you can mediate those. I'm not gonna read all that. Okay, a word about joint code ownership. This is a really, really big deal here. So what you're looking at is my kind of, I don't know, satire here. PagerDuty is an online service that will just annoy the living hell out of you if you're on a PagerDuty rotation. Basically, if a system goes down and you happen to be on call, PagerDuty will page you, it will call you again. It will have a little computerized voice that's super annoying, and the last thing you want to do is see this number. It's, you know, it's like a 415 Valley area code, just the worst. And my point here is that if, as a data scientist, you think, well, this is my code, I don't, you know, I'm going to own this code, I'm not really going to collaborate with engineering. You own that code exclusively. Are you really prepared to sign up for PagerDuty? Because when the system goes down and it's a model-related problem, guess what? You're the only person walking the earth who can troubleshoot that. Do you want to be the only person responsible for a production system? The answer to that is I don't think that you do. If you think that you do, I think that you're mistaken. Because when you're on vacation, you're never on vacation. And I was this person. I was responsible for production systems, and for a while I was the only human on earth who could deal with certain problems, and I was never free. I was a slave, and you don't want that. So the topic of joint ownership is huge. If you're building something that is meant for production, it's going to land in a production system, you want to work with another data scientist, and you also want to work with your fellow engineers, your software engineers, so that the code that is developed is considered jointly owned. So that if there's a problem with it, somebody else can troubleshoot that problem. And they don't just say, oh, it's a black box, it's not my problem. Call Joe, call Jane, not my problem. So one of the ways you can deal with that, and this is the way that you know, traditional software engineering, one of the ways, it's a very good way, is to pair programs. That means you sit down with your fellow engineer, your fellow data scientist, you work together on a common code base. And this is where notebooks are just going to fall right on their face, because, you know, I don't know of a software engineer, I just don't know of one who'd be like, no, let's definitely use a notebook for that. They'd be like, no, we're not using a notebook for that. We're going to do this, you know, the way all the other software runs. Your code isn't any more special. It doesn't, you know, doesn't belong in, you know, a special IDE. It's code. It needs to be treated like just like all the other code. So we're going to put it in our repo. It's going to be in .py files. We're going to test for it. We're going to lint it. We're going to format it, you know, and we're going to jointly own it. And we're going to work together to make this viable code for production. And we're going to do all the things that we do with other software. And we're going to respect the differences in data science. We're going to help you. You know, we're not going to judge the code, but we're going to work together to make it good. All right, I'm just about finished here. So let me run through these last things, and then we can, because I'd like to finish, I guess, and technically I have till 7:30, but I really want to finish closer to 7, so we can do whatever we want to do here. So here is my advice to a data scientist. Here's the do's and the don'ts. And please take this with a grain of salt. I know that my communication style tends to be a little bit on the dogmatic side. Take that with a grain of salt. You know, at the end of the day, every situation is different. I don't know everything. I don't know even a fraction of what I think I know, in fact. So ultimately, you want to experiment, try things, try processes, but be aware of these topics, be aware of the issue. So I'm going to lay down the do's and don'ts, but take this with a grain of salt, please. Okay, so advice to data scientists: it is your responsibility to bridge the gap. That's the thesis of this entire presentation. I've hidden it here in this one bullet point, but that's the conclusion. How do you bridge the gap? It is on you, data scientists, for the most part. So I'll fill that in a little bit more in the conclusion here, but that's the spoiler. Okay, be wary of long running notebooks. If you see code that's sitting in a notebook saying that's my code, be very, very wary of that. you want to move that code out of that notebook. Now, I would suggest you have a rule, which is I just use a notebook as an ephemeral tool for evaluating code much in the same way that somebody would use a REPL, a REPL, read-evaluate, print loop. When you go to Python, that's a REPL, right? You type something, 1 + 1, hit enter, it's 2. Reading, evaluating, printing, looping. If you use a notebook that way, there's no temptation to create this, this high ceremony, lofty, long-running artifact. You're using it to experiment. You're using it to get insights, but then you're copying that code over. As soon as you are comfortable with it, as soon as into a script, module, etc., that you can run in this iterative fashion. That is a hard problem. What I'm suggesting here is hard. And I don't think that it works smoothly, but I think that it's the right today, as of this moment, I believe it's the right workflow. Jeremy Howard has been going the other direction, and very few people I respect more. He's the reason, basically, we're doing this online meeting, for better or for worse. So I hold him in very, very high regard. He's going to the other extreme, where he's actually, modifying the notebook to be a better IDE. So, but I think for most production shops, that is the wrong advice. I think he's wrong about that. I think for more ad hoc, casual use, students, his primary audience, where he is teaching students, and they are moving things from a learning state to more an increased production state. That's fine. But what I'm talking about is an organization that's building data-enabled software. I don't think that his suggestion is viable in that environment. So my advice: beware of long-running notebooks. Work very closely with engineers early in a project. Don't do your work and then expect to do an integration smoothly down the road. Much better to start right away with the engineers, talking about the issues that I've enumerated in slides before. Key metrics, how to run things quickly, how to capture results, how to be iterative, share joint code ownership. Do that early on. There we go. Good advice. See best practices. Yeah.
Are data scientists delivering notebooks as the requirements, or something more evolved?
That's an interesting question. I don't like the word. You don't often hear the word requirements, because of Agile has sort of just completely swamped the idea that there is a requirements phase. And I'm not sure what you mean by requirements. I assume it's sort of a specification. Let me interpret that question a little bit. I think that there could be a use of a notebook for purely documentation reasons. It's nice because you can execute it, but if it is for purely documentation purposes, I could be persuaded. The alternative to that is actually a method that we've been using at Guild, which is to invert this, very much the way R works, our studio and our Markdown, which is I take it back. It is not that. So this is a bit unique. It is the way that we do it is we will actually invert that problem, put the documentation in doc strings in a Python module, and then generate a website using that PDoc tool. So we can test and generate documentation, but all of the artifacts are in .py files. So the notebooks are vestiges. We don't like to see them, and if we see them, we move off of them as quickly as possible. Sure, they end up living in a repo for a while, but they become dead code. I don't know if that answers your question. We can revisit that. I'm going to finish up. I just have 2 more slides here, and then we can be officially done, and then we can have discussions, quote unquote, offline. It'll be online, but we'll be done, and we can continue. Okay, so we'll come back to that if need be. So the don'ts. Don't tolerate this gap. This is, I think this goes for both sides. There shouldn't be a gap. That's really the point of this presentation. The gap can be closed through concerted effort, but the first step is to not tolerate it. There should be no gap. Number 2, don't. This is a don't, by the way. Don't assume exclusive ownership of your code, and please do not disregard production concerns, because what will happen is you will be on the beach with the pager as noted. And that is, Just no way to live. No way to be on vacation. And engineers actually have a lot of work here. I say that the data scientists are responsible for bridging the gap. What I mean by that is the data scientist, what I'm saying here is a data scientist should assume the practices of the engineers. Engineers are not going to assume the practices of data scientists. They're going to have to stop their work and go to school for a couple of years at the graduate level. It is. If I had the time, I'd go research. I'd go publish. Like, I believe this is formidable intuition tells me. It is much easier for data scientists to adopt and assume best practices in software engineering, by far much easier than it is the other way around. So I feel that it's incumbent on the data scientists to change the practice to become more like software engineers. Now, having said that, here's what I'll say to the engineers. Appreciate the impossible job of a data scientist, and it is a really rough life. It's a rough job. Much of your work is discarded. The results are never as good as hoped for. The expectations are always unreasonable. 100% of the time, you're never going to meet expectations. It's a very frustrating life to live because, 80%, I was kind of hoping for 85. And you're just like, no idea what I just achieved here. So you're always being criticized, never being championed. And you're tasked with the very hard problems to begin with. And now I'm suggesting all of the software engineers work as well. So software engineers, appreciate this and be empathetic. So build, and then having said that, build positive and helpful relationships through pair programming. So that is working very closely with data scientists in code development, and help to automate, test, and track experiments. So try to assume as much of the burden off of data scientists from a tooling and process standpoint to make their work easier and faster. But still, their goal is to write and maintain code in the same quality, the same process that you do. Don't criticize their code. Don't criticize their code. There's no place for that at all. There is no such thing as bad code, especially from a data scientist, and I mean that. If the code works at all, it's beautiful code. And your job is to sensibly refactor it in a way that fits the regime that we described before. You can help them with that. And the idea is that in time, that data scientist will become better at writing the code that is the long-running code. And there'll be less refactoring and less rework. But that job, that it's incumbent on you, software engineer, to nurture that development without judgment. So refactoring and rewriting with wait a minute, these negatives here. So don't criticize code and do not refactor or rewrite code without close collaboration. Let me explain this last one. What I mean there is don't go into a corner and rewrite all the work and say, hey, look what I did. It's completely different. The data scientist needs to participate in that process, or they won't recognize the code. And they'll be like, this is not my code. I hate this job. I'm going to quit. So you want to work closely with them so that they feel like they own the changes. And if they're uncomfortable with something, you stop and you agree with them. You defer to them, or they are in charge of that process. But understand them. I'm also talking to them. They have to understand that in time, that code needs to move into a production state. So it is very much a collaborative process. I encourage the engineers to be light on the judgment and really heavy on the help and support and patience. Last point, we're gonna finish up here. Advice to managers and stakeholders. This first point here, combine your teams, is something that I've never seen. I've never seen it. So I know that this is a controversial point. I know that this is a crazy idea. I don't believe that data scientists should neither be physically separate nor organizationally separate from software development. If your organization is building software with data science input, right? Some organizations don't do that. But historically, data science functions are organizationally different. It is a bad structure, and you will not deliver software as quickly, and the software will not be as good. And I am tapping into a long line of software methodology points here. I'm not off in space. This is a not incontrovertible point. It's the centerpiece of agile development, where you co-locate stakeholders, you co-locate different functions on the same team. So I would encourage, can't be done overnight, but think about ways to bring the teams together to work closely together. 2, consider it a double expense. Data scientists and engineers as a pair. Don't think of them as one or the other separately. Think of them together and pay for them together. Ask early on, what is our measurement for success? And keep asking that so that your team understands that that's an important question. And finally, support ongoing iterative improvements driven by these success metrics. Don't do the following. Don't be deceived that paying double is actually costing you double. It's actually cheaper. By investing in the proper collaboration, you will get much better results much sooner at a much lower price point. I don't have a lot of studies on that, but that's true. It's a true statement. You will pay more in the long run if you separate these concerns and expect there to be an integration that isn't incredibly complicated, painful, and ultimately non-productive, because it will be. And finally, don't forget that data scientists are prospectors that rarely strike gold. Be understanding of that and lighten up a little bit on your expectations, because it is a very, honestly, in all seriousness, it's a very hard job. And there's a lot of data scientists who get into the field and they burn out and they leave. And there's no reason for that. There's no reason at all. This is incredibly challenging work, and data scientists need to be supported both from an engineering standpoint and a management stakeholder understanding standpoint. And there's no reason not to do that. Just understand what's going on. You need to understand the process and support it. Okay, almost done. This is the gap. Right? That was our original problem. We see now data scientists need to go over to engineering. It needs to look like this. That's the answer. But really what we're talking about is this. Everyone under the same roof, much love, iterative collaboration. This is old-fashioned teamwork, and this is the gap. So there's no gap. We're bringing folks together. They're working together, using the collaborative underlying methodologies famously successful in software development. So that's why I'm asking the data scientists to move into the engineering camp. Okay, so with that, I'm officially done. We can open this up for discussions for those who want to remain.
I have
and then those who want to peel off can do that, and we'll have it recorded.
I have a small question here that I want to address.
Mm-hmm.
Okay, as the analytics industry, well, if you can mute yourself so we don't have echo. As the analytics industry matures, we are finding it more difficult to draw the line between data science work and software engineering. For the time being, it seems that adherence to best practices like PIP-A, .py scripts over Jupyter notebooks and Nextest is an important step for many data scientists. Do you think it will be necessary in the future to lean in more heavily on data scientists with strong software engineering skill sets to deliver production ready to work, or do you rely on software engineers hires to close the gap?
Well, this is a great question because it will allow me to restate my summary here. I don't think that it's fair to ask of a data scientist to become an engineer entirely. This is not, I'm not suggesting, I'm not saying that a data scientist needs to become a software engineer. What I'm saying that a data scientist needs to understand what makes software successful, because they are building software. I don't know what's going on here. So I think the answer here is you don't want a gap. The gap is false. So if your methodology is in sync, right? So that you're in the methodology, I'm being very specific here. I'm saying the methodology should be this automated, iterating, so rapidly experimenting, testable process, which resembles test-driven development. If it's that, there really isn't a gap. The two sides work together very seamlessly. I've seen this over and over, and it gets hard to get there. It's a cultural mind shift change, but the mind shift change is primarily in the mind of the data scientist.
What is a specific example of testing in model development?
What was that?
What is a specific example of testing in model development?
Yeah. So what is an example of testing in model development? Running a training operation on a particular data set and asserting the range of accuracy. And you can't peg the range. You can't say it's going to be 88.3 unless you're trying to do bit level reproduction, and that's not a good idea. You want to allow variation. Now, I feel like this question is actually could be a field of research, because it's very difficult to make an assertion that should be between a certain range, because there's statistics involved here. You're going to have a certain number of occurrences where it won't be. There's going to be variation in your output. It's the nature of the beast. One of the things that we've been looking at is using anomaly detection to measure outliers. So there are different models and different approaches to measuring anomalies or outliers. And so we can look at the output generated from any of these operations and treat them as outputs of a process. We can model that process, and then we can state with some degree of certainty, these are all probabilities, that a given outcome is an outlier. That would be a test failure. So you might say, over time, we're going to measure the accuracy of a particular model. This assumes a certain stable state. So I mean, this is as something matures and moves down the road and is probably nearing production or running in production. I think it becomes important to start to be a bit more sophisticated. So long-winded answer to probably the right answer is start with the obvious things, like we expect accuracy to be above this level. If it isn't, we have a failure. We expect some other metric, a statistical measure associated with some sampling. You'll do a random sampling of a data set. We expect it to fall within this particular range. Those are different ways that you can be very specific about checking your assertions. A lot of this is going to come down to the data scientist reasoning about what are the ways that we can catch bugs. And so I feel like this is a new area. This is an area, but whatever it is, whatever the answer is, you got to measure it, and then you've got to make an assertion. And so that's where it fits nicely into the traditional TDD format. But that is a very good question, and I think that there isn't a simple answer. And I think it can be very simple, naive, and it can be very, very complex.
Thank you, Garrett. We have a question here. It says, as I apply to data science position, I'm beefing up my project. Beyond spinning, you allow etc. What, in your opinion, does a production-ready data science project look like for someone in job hunting?
Yeah, that's a really good question. I wouldn't worry about EC2 instances, certainly. You can do all this work on your laptop, so that would be one thing. The long-running processes, everything that I discussed here can be done in a very, very small scale. And really long-running processes, they're going to teach you patience. That's what they're going to teach you how to wait. So I would try to pare your problem down to shorter problems. What I would say is this. I would say, pick up a Kaggle competition and use the methodology, that I'm proposing here, which will be sort of this experiment-driven, you could almost call it experiment-driven development, where you're iteratively changing and experimenting with things, but you're doing so within a test measurement regime. So I would push those things forward. I would certainly be writing in Python files and trying to get your code. I would try to find some software engineer colleagues or friends, pair program with them. I would start using linters. I would start writing tests for my code. Start to do the things that software engineers do to improve the quality of your code. That is really going to differentiate you significantly. And then there's no substitute for, I mean, if you can run the simplest thing in production somehow, I mean, I don't know how there's no substitute for not just putting in production, but seeing it through an evolutionary change. So you add a feature or you fix a bug. Seeing that will differentiate you from, I think, 9 out of 10 data scientists. So I would give that advice for everybody, not just those looking for jobs.
Is there any good online resources or material on good software practices?
Oh, online. I was just going to think of the libraries of books that you could get. Honestly, I would get a book. I would go on Amazon, or I mean, if that's tough, maybe find a library. I mean, what you're asking, the answers to this are going to date back decades, so you don't have to get the latest book. So I think your local library would have good books. I don't mean to say, oh, just go to the library. I mean, I have a whole bookshelf full of things here. They're old. But I haven't, I'm not naming certain ones because certain ones aren't. I can tell you the ones I like. They're down here someplace. I have to go look for them. But I would read books, and I would stay away from blog posts. I would stay away from anything on Medium, because it's almost certainly not very good. Seriously, it's almost certainly not very good. But the stuff in books, especially famous books, so maybe go on Amazon if you can afford it, buy it, patronize the author. If you can't, try to find it from a library. That's what I would do.
Sounds good. We don't have any other questions so far. You're mute.
Okay, well, good. So we're almost 7:30. So that my hope to end early worked, but not as early as I wanted to. Fine. Thank you very much, everybody, for joining us in this experiment. And yeah, Clean Code is a very good book. Scott McConnell, I think. That's one of them on my shelf here. I think it's his book, right? Clean Code. Scott McConnell, Andrew. Anyway, yeah, and you know what? We can, this is a really good topic to continue discussion on the Chicago ML Slack. If you're not already on there, it's bit.ly, so it's a bit.ly URL, and it's just Chicago-ML-Slack. Super easy to get to. Join in, come in there, ask these questions, and that would be a really nice discussion topic for folks on Slack. Okay, let's finish. Thank you for engaging in this experiment, the socially minded, responsible experiment that we're running. I expect to have another couple of meetings in March. We're going to run the same format. We'll have to work with the other speakers. I'm not going to be presenting, so there'll be other speakers. But the fun thing is I can imagine workshops running this way and other things, and we can involve people from other cities. So there's all sorts of upside. And of course, we will meet again. We will all meet again face to face, which is also important, but maybe not in this very moment. So with that, I'm going to stop our recording and I'm going to stop our meeting. And thank you once again.